Hi guys, hope you are doing great in your life. So this is the second tutorial video on ZYNQ SoC. Hope you watched the last one where I showed you how we can use the ZYNQ SoC to print the hello world using VITIS 2025 versions. So in this video we will be discussing about how we can integrate the FPGA part and the processing system part together. So let's see. Okay, let me just open the paint and don't yell at me why this guy is using still paint. So this over here you can see this is our ZYNQ SoC system on chip. That means everything we have included in the system, that is UART, SPI, ADC, whatever, and anything else. Lot of things we have, but we will not be discussing about all these things in this video. So here you can see this is the programming logic. This complete is a one silicon die, and in this we have the programmable logic, that is the FPGA part where LEDs and everything will be there. This is the processing system. Processing system means we have over there this itself means it is a CPU. That CPU itself is integrated in that programmable logic, or we can say in that same silicon die. Over there you can see we have the input output block, the external input output block, which is connected to the processing system also, and the programmable logic block also. So you can use the programmable logic, that means completely FPGA with the input output block easily, just like you can program any other FPGA. That is fine, it will work fine also. You can use the Python part and you can program this programming system, processing system, and you can still use the input output ports, input output blocks, or GPIO pins, and still it will work fine. The main thing is how we can integrate these things. Suppose how you will share the data from the programmable logic from the LUTs to the processing system, or from the processing system to the programmable logic. That is the main thing, and here we will do this thing using a SKY protocol. This internally will manage all the things. We will see how we will do that. Okay, so let's go to that example. So here today we will discussing about how to integrate this programmable logic and the processing system in the full half adder. So my pink Z2 board, initially I thought to make full adder, but I only have two switches, so that's why I shifted to half adder, that is A and B. So in B, as we all know, that sum is just a XOR of A and B, and carry is just the AND operator of AND gate of A and B. Fine. So this is the other implementation of half adder itself. You can just verify this by yourself. If the output of the XOR gate is again inverted, and again I'm just doing the AND of that output, then it will give the carry on itself. Why I'm doing this? Because I have to show you, not them. So I have to show you how you will take the output from the programmable logic, and then you have to integrate that output. You have to pass that output to that processing element. That is the main agenda of this video. That's why I have just modified some integration of like implementation of the half adder, but the functionality will remain same itself. So today we will do this half adder part in the programmable logic, that is in the FPGA part, and this NOT operator, NOT gate, and this AND gate we will do in the processing system itself. So in that processing system, we will have two inputs. That one is this XOR input, other one this one, and we'll just name it as one. This one is second. So in total, we have two outputs also. I'll just change my color to yellow or blue something. So this is my first output, that is sum. This is my second output, that is carry. Hope this part is clear. This verification, this implementation, you can verify by yourself. That I will not do. This is not a theory or the digital system design class. So let's work with that Vivado part. So this is the Vivado 2025. I am using pink board. If you are not aware how you can use, which board you can use, and how to make that, how to add that board files, you can refer my previous video, which there I have mentioned and discussed detail about that. Here I will not do that again. So what is my project name? I will just name it half adder. Half adder using SoC. Fine. And let's go ahead. RTL project sources, this we can create later. Constant file also we can create later. The main thing is you have to select your board. So right now I'm using the pink Z2 board. Let me just check pink Z2 board. Okay, fine. Yes, and finish. So let me just check recording is going on. Okay, fine. Everything is fine. Hmm. So first we will be making the XOR gate. So I'll just make create design, create, that is main dot v. We also you can write finish. This is main. Here also you can give input output, but I don't prefer that thing. Prefer writing over there. So in this we will have input a comma b. You can name anything, and when we have one bit output, that is, you can say sum, or here I'll write y also. Clear? Then you have to write the code, for example, zor g1, and then we have y comma a comma b. This is gate level implementation. You can do anything, you can write anything. Other implementation could be this assign y is equal to a or b. This also works fine. Anything you can do. This is your thing. This is not the again digital design class. Fine. So this is our code, that is main dot v. Now we'll move this thing to the block level. As we have discussed previously also, whenever we have to use the SOC part, we have to go to block level designing. Otherwise it is very difficult. So let's go and create block design. And okay, before block level, I'll prefer to make the constraint file. So let's add the constraint file. Create or add constraint file. I'll create one constraint file. I'll name that physical underscore constraint. That is fine. Okay, finish. And I will give this link to you. This is the constraint file for Z2 pink Z2 board. Based on that, which board you are using, you can find that same constraint file. Now I'll just copy paste all this content. Paste. I will turn off everything, comment out everything. What are the things I need total? In the constraint file, I have to define everything as a complete silicon dia, because this complete is silicon dia, right? So how many? Two inputs I have. This, I'll change this color. This is one input. This is second input, and two outputs we have, sum and carry. We are not worried about this intermediate outputs right now. So that will discuss in the, because in the final inputs and outputs has to be LEDs and switches, right? This will be connected to switches, this will be connected to LEDs. So that we have to define in the constraint file. Let's see how. So here if you go to this is two switches we have. I'll just uncomment these lines. Two switches we have. One is M20 and M19. If you just go to the manual of that, okay, where is that manual? Just give me a minute. In my history I have that manual. PDF pink. So this is the manual, and over there you can see two switches we have in the pink. This is the pink Z2 board. This is two DIP switches. These buttons are also we have, but I'm not going to use the buttons. Only two switches we will use, half adder AB, and these switches are this M20 and M19 as mentioned in that constraint file. Okay, fine. So what are the values of the switches? Here the thing is, if you are programming normal FPGA, right, you will directly give this A and you will give this to B, right? But here we will not do that. Here things will be different. Let's rename it to any other thing. It is SW0, SW1. Is this clear? Because here my input name is A and B. Later we will modify this thing. I'll tell you in the block diagram. We will connect this A and B to this SW0 and SW1. Fine. Now I need two LEDs also, so I will use these two LEDs. You can use this RGB LEDs, whatever you want. So again I will just name it as sum, and the other one I will name it as carry. This is our final output, right? These things are not defined. This sum and carry and SW0, SW1 is not defined over there in this main code, right? Okay, I'll explain you how you will connect those things. Just remove extra things, then save the constraint file also. Now directly go to the open block diagram. Where is our block diagram? Add the ZYNQ SoC first. ZYNQ processing system PS. It is done, and as you know, whenever it is there, we have to connect the reset and clock signals. For that we need processor system reset. That is already included. Now the thing is, we have to connect that RTL code. We have to import that RTL code over this block diagram. How we will do that? Directly click on this RTL code. This is our main RTL code, main.v. Over there you can see. Right click it, and here we will have the option add module to block design. And then if you go to this design, this is your RTL code. We have A and B over there. A, B and Y output, right? And keep it over here. Next, what we need? We need one AXI GPIO connection. So that's what I told you over here also. So whenever we have to connect this output, this programming logic output or input to the, whenever we have to interconnect these two things, we have to use this AXI GPIO port. So where we will use that, one port we will use here for the inputs, here and here we can use same ports, and we can use different ports also, no problem will be there, and one port will be here. This output of the processing system will go to that AXI GPIO. So one port for the input and one port for the output. Let's see how. What is this? I'll just add again AXI GPIO. This is one. Again I will add one more AXI GPIO. Done. You can add n numbers of GPIO ports. No problem in this. Okay, so right now over there you can see it is using the GPIO connections are, it is not working properly. We have 32-bit 32-bit. Okay, we will not use 32-bit, only we have 1-bit data, right? So I will just modify this property of this. You will have to go to IP configuration. So first, that's what I told you, this same port here I will use same port for the input. So I will define it as all inputs we have 1 bit, and here you can use 2 AXI for inputs. I will use single only, but I will use the dual channel. All inputs 1 1. Understood? Got it. Now we have, if you just see here, we have two inputs, GPIO and GPIO2, two channels we are using. This is 1-bit input, this is 1-bit input. From this triangle also you can see this is the input signal. Next we have 1-bit output, right? Okay, here you can see this is 1-bit output only, right? This output we don't need, because here, okay, someone is saying why we don't need the AXI over here to give this output, right? Because this is already in the programming logic. Programmable logic is directly connected to the input output port, but processing system is not. So that's why we need the AXI over here, but we don't need the AXI GPIO block in this thing. So now I'll just change this setting also. All output, here I will be using only one port. This bit width is 1. Done. Now how you will define that? Okay, this A and B will be coming from the outside environment, right? This A and B is coming from the outside environment, that is from SW0, SW0 and SW1. So let's make it external. Right click it and you can do Control T. Otherwise you can right click and this make external. Done. Now here the names are different, A0 and B0, but now here you have to change these names to whatever you have mentioned in the constraint file. What is the name? SW0, SW1. So here we will link those things. So here, from here, this external port property SW0, and then this to SW1. Understood? This Y also you can make to external directly. What is this? Make external. And this, what is this Y? This is XOR, right? Then this is sum. This is sum. Now we have some output directly from this RTL code itself. Now if you see this diagram, I'll just remove redundant things. Just give me a time. If you see this diagram, I told you we have one AXI port over here, same AXI over here. This is first channel, this is second channel, one AXI port over here. AXI will represent like this cross. This is first, second as input. This is single channel itself, that is at output. So the same output will go to that output, that is sum, that we have already routed. The same output will go to the input of this AXI port, AXI GPIO. So I will connect this output, suppose this same 0 1, no? This to this thing, and what is the next output? Next input. Next input is the A1. Okay, I'll just verify it. Is it A or B? Okay, this is the A only. So next this I will connect to A. So this you can connect manually. You have to connect manually itself because that the border does not know how your circuit is working, right? Now this is done. Now we have one output port. Let's keep it over here. Hmm. Now we have to make this external also. This is one bit itself. So let's right click and make external. Okay, so this is a wrong implementation of making it external, because like this it will make at bus. This port will be a bus port, not a single wire. So first expand this thing, then you click on this wire, then you make this as external. Then this will be 0, 0, that is one bit. And what is this? This is carry. If you are saying here, we have one difference over here. What is the difference between AXI GPIO ports? This is AXI GPIO 0, and the other one will be AXI GPIO 1. So this will be the differentiator when we are writing when we have to write the C code for this. Then like this only we have to differentiate. 0 port, first channel is the sum output, second channel is the A output, A input, and then AXI1. AXI1, we directly call AXI1, that is the output port, right? Rest no things you have to do by yourself. I'll just run now. This is our main connection that I have already done. All the connection Vivado will do by itself. You just click on this run block automation, select this thing, disable, fixed IO DDR, fine, okay. It will take some time. Done. Now you have to do the run connection automatically, select everything, and okay. Now it has done all the connection automatically, but the main thing is this main RTL is directly going to this sum, that is this is FPG only. This FPG output is going to that the AXI board, and then this AXI is connected to this smart connect. Previously it is interconnect, but now in Vivado 2024 and later versions it is smart connect. So this will be handling all the AXI. What do you mean? AXI data and address, everything it will handle automatically. We will not care about these things. Then from here it will go to the processing system, and again processing system will give the output to this thing, and then this will give the output to our this GPIO1, and GPIO1 will give the output to carry. This is our main block. So now this is done. I will just save it. Then you have to click on this validate design. F6 is the shortcut key. I'll just click it. If there is any error, it will show the error. Okay, run successfully. There is no error in this. Now I will just generate a bit stream. Save. It will take some time depending upon your computer. Maximum number of job 20, and that is done. Now I will just pause the video and wait for it. Okay, so I forget completely one step before doing this. I am right now I'm getting the error because it is generating this. Hmm. Because it is generating this bit stream for this main.csv, but main.v, but we don't have to do that. So we have to make a design wrapper for that. So this complete block diagram we have to convert to Verilog. How we'll do that? Right click on this, create HDL wrapper, auto update. Now it will write the Verilog code for all this design. It is already there. It will not take much time. You just have to set it as stop, and over there you can see it will be using everything. Our main code also, this is our main code. It will connect everything, and this is our main uh, code. For this we have to generate a bit stream. Now again I will pause the video for some time, then this bit stream will be generated successfully this time. Okay, so now as you can see bitstream is already generated successfully. We will not open this design and all. Just you can see. So now as you know, okay, we can program this FPGA because if you we just go again back to this diagram. This complete part is programming logic, that is FPGA itself, right? So our sum will be working properly. It is just a XOR of A and B, but this carry will not work here. Will not work yet. So I'll just test it. I'll connect my FPGA. It is connected now. I'll open the target. Okay, so this is opened. I'll program it. Design one wrapper dot wait. Fine. Program. It is done. Now if I turn on the camera, just give me a minute. So now over here you can see my camera, and this is my FPGA board. So this is my this LED is representing the output sum. This is representing the carry. These are the two inputs. So 00 is 00 itself. 01 is sum is 1, carry is 0. 10 is sum is 1, carry is 0. And 11 means carry has to be 1. Sum is working fine. Carry has to be 1, but it is not there because that processing system we have not included yet. So I will now just stop the camera. So after this you have to, if you are already seen my previous video, then you know, okay, you have to go export as hardware. Next, include bitstream. Okay, include bitstream. Design one wrapper. Fine. The same folder. Fine. Finish. Now it will create a .xsa file, that is your hardware design file. After this our Vivado steps is completed. Now we will move to Vitis IDE, and I will stop this video. I will make a part 2 for that because this video is already 22 minutes long. So let's stop this video. Bye for now. Have a great day.